For the capture and analysis of satellite images, various wavelength ranges of the electromagnetic spectrum are important. Infrared plays a special role. Most people are familiar with infrared from everyday life. Thermal cameras, infrared lamps, and even remote controls use infrared. We humans cannot see infrared, but we can partially perceive it as heat. So what exactly is infrared? Let's take another look at the electromagnetic spectrum. The infrared range in the electromagnetic spectrum is bordered by visible red light and microwaves. Electromagnetic waves with wavelengths between 0.78 micrometers and 1 millimeter are referred to as infrared. Since this range is relatively large, infrared radiation is further subdivided into near shortwave, mid, long wave, and thermal infrared, as well as far infrared. Apart from far infrared, all these ranges are used in specific remote sensing applications. For instance, water vapor absorbs certain areas of the mid and shortwave infrared particularly well. A circumstance that allows meteorologists to use these wavelength ranges to determine the water vapor content in the atmosphere, assess humidity, or track air movements. The same effect also plays a crucial role in the processing of satellite images. Because the water vapor in the atmosphere absorbs and scatters certain parts of the electromagnetic spectrum. This happens both on the way from the Sun to the Earth and from the Earth to the satellite. And thus, information reflected from the Earth's surface is distorted. However, the water vapor content in the atmosphere can be determined using near and shortwave infrared to perform an atmospheric correction. Now, the satellite image can be used for analyzing the Earth's surface. This satellite image from the ISS sensor HICO shows an algal bloom in Lake Erie and illustrates another important application area of the infrared spectrum. Because vegetation on land and in the upper layer of water bodies can also be examined with infrared. In this case, near-infrared is used, which is particularly strongly reflected by plants. It is reflected by chlorophyll, the green pigment in leaves. Plants absorb blue and red light, which they use for photosynthesis. Near-infrared and green light, on the other hand, are useless to them and are reflected. This results in the leaves of plants appearing green to us. In healthy plants, however, this also leads to a sudden increase in reflection, from red to near infrared, which we refer to as the red edge. Remote sensing uses this phenomenon to calculate the normalized difference vegetation index, or NDCI for short. The NDCI is the quotient of the difference and the sum of the red and infrared channels. The more vital the observation of vegetation is, the closer this index is to 1. Low or no photosynthetic activity is indicated by a value close to -1. And the NDCI is just one way to make precise statements about the plant world from satellite images and the infrared spectrum. For example, another index, the leaf area index, LAI, provides information on how dense the vegetation cover is. The use of thermal infrared turns the basic concept of remote sensing on its head, because normally the sunlight reflected by the Earth is depicted. However, with thermal infrared, the heat radiation emitted from the surface is particularly interesting. Surfaces and bodies emit heat, among other things, as thermal infrared radiation, which theoretically makes it possible to measure temperatures from space. The problem is that different surfaces emit this long-wave radiation differently. Well, for example, a metal roof at 30 degm will emit less thermal radiation than a tiled roof at the same temperature. Water vapor and aerosols in the atmosphere also obscure the Earth's surface thermal radiation. And yet, after atmospheric correction and alignment with surface maps, one can deduce the temperature of the recorded surfaces from the intensity of the thermal infrared measured in the satellite image. This results in images that allow surface temperatures to be measured across the entire globe, all without a thermometer. But wildfires and other heat sources like volcanoes can also be observed this way. Infrared plays a central role in remote sensing. It allows us to make more accurate weather forecasts, monitor various ecosystems on our Earth, provide temperature data for climate observation, and gives us a glimpse into the diversity of our planet, beyond the visible.